Hi, welcome back to 101 Things. Today I want to share with you the build of an SSTV decoder using a Pi Pico. It's a super simple design that needs a Pi Pico, a cheap TFT display and a couple of resistors and capacitors. It supports Martin, Scotty and PD modes, and it works with pretty much any receiver just by connecting to the headphone socket. I'm going to talk through the build, tell you a little bit about how it works, then we'll see if we can receive some signals. If you haven't come across SSTV before, it's a very simple method of transmitting images using a narrow bandwidth voice channel. It's been around for a while. These images of the Apollo moon landings were sent back to Earth using slow scan television. By the early 70s, radio amateurs could buy slow scan television equipment like this, but it was very expensive. This unit would have cost about $295, which is over $2,000 in today's money. Even though it's been around a while, SSTV is still very popular on the amateur radio bands. During the daytime, especially on holidays and weekends, there's a more or less constant stream of images being transmitted on the 20 meter band. The usual setup is to use a PC with some SSTV software connected to a transceiver using a sound card, but microcontrollers are pretty powerful these days, and it's easily possible to decode these signals using a Pi Pico and the built-in ADC. Once you've built the SSTV decoder, you just need a single sideband shortwave receiver. If you don't have a suitable receiver, why not check out the Pi Pico RX? It's a cheap and easy to build receiver based on the Raspberry Pi Pico. Let's talk through the hardware design. I'm using the Pi Pico's built-in ADC to sample audio output from the receiver. The Pi Pico can work up to 3 volts peak to peak. This means it can handle the voltage from the headphone output of most receivers and doesn't really need any extra amplification. I just use a DC blocking capacitor and a potential divider to give the ADC the right DC bias. I'm using an ILI 9341 display with an SPI interface. This type of display is cheap and easy to get hold of. They're also available in a few different sizes. The one I'm using is 2.4 inches. You need to get one with an SPI interface and make sure you supply it with the right voltage. Most have a jumper you can short out to bypass a regulator so that you can run them from a 3.3 volt supply. That's how I've connected mine. The display uses a 4-wire protocol based on SPI. It's only unidirectional, so you don't need to connect the MISO signal. I've also hardwired the reset pin to 3.3 volts to save an extra pin. I've written the code using C++, but to keep things simple, I've provided a simple demo application as a sketch in the excellent Arduino Pico port by Earl Filhauer. This is probably the simplest way to get a C++ development environment for the Pi Pico up and running. It only takes a few minutes to install the software and run some demos. I've added a link in the description. There's quite a bit of variation in the TFT displays, so I've added some compile time options in the sketch. You should be able to change the rotation and colour settings to work with most ILI 9341 or 9342 displays. Now, let's quickly look at how the software works. There are quite a few different SSTV standards, but Martin and Scotty protocols seem to be the most popular. I also found that there were quite a few signals using PD50 and PD90, which is probably because they're quite a lot faster. SSTV signals are designed to work over narrow bandwidth voice channels. They use frequency modulation scheme where the intensity of a pixel is represented by a tone between 1500 and 1900 Hz, with 1200 Hz horizontal synchronization pulses between each line. Each image starts with a vertical synchronization pulse followed by a VIS code. The VIS code is a 7-bit number that can be used to work out which standard is being used. The different standards are all fairly similar in structure, but tend to have differences in timings. For example, Scotty is very similar to Martin, but uses a slightly different length of colour line, and the horizontal sync appears in the middle of the line between blue and red, rather than at the end. The structure of the software is fairly simple. The first step is to convert the real signal into a complex signal, and then calculate the phase of each sample. I reused the Hilbert transform and Cordic code from the transmitter project I did last year. Once we know the phase of each sample, it's easy to work out the frequency by calculating the change in phase from one sample to the next. I scale this to provide a frequency in Hertz and apply a low-pass filter. I then use a state machine and some counters to work out the colour and intensity of each pixel based on the frequency. To start with, I used the VIS code to work out which SSTV standard was being used. but I found that the VIS code was a bit unreliable, and if I missed the VIS code, the whole image could be lost. I found I got better results by guessing the mode from the interval between H-sync pulses. This means the decoder can reliably detect the mode, even if we miss the start due to fading. Another feature that I found very useful was automatic slant correction. If there's a difference between the sample rate in the transmitter and the receiver, then slant can occur. This can be corrected in the receiver by measuring the average interval between horizontal sinks. The timing of the receiver is adjusted accordingly. It does quite a good job of correcting the slant from poorly calibrated transmitters. But for well-calibrated transmitters, it can make things slightly worse. If you'd like to find out more about the technical details, take a look at the documentation. There's a link in the description. I built a simple test harness so that I could try out the decoder using generated images and recordings. I've done a fair bit of testing now, and I seem to have a solution that works quite well. Now I'm ready to try this with signals off the air. I've left the decoder running for a few hours, and I've picked up quite a few images. Well, I'm quite pleased with the results. It's fun to just leave the receiver running in the background and watching the images coming through. I decided to design a simple 3D printed enclosure for the project. I've added a link to the STL files in the description. So, that's it. We've built a really simple SSTV decoder using a Pi Pico, an inexpensive TFT display, and a couple of resistors and capacitors. In future, I'd love to make some improvements. I might look at adding support for more SSTV modes, and maybe add an SD card so that I can save images. Now we have the receiver part worked out, it should be quite simple to implement the transmit side. I think it might be fun to add a simple camera module so that we can also capture and transmit images too. If that's something you're interested in and you'd like to see more, why not subscribe? I've got lots more ideas for projects that I'd like to share. Thanks very much for watching, and I'll see you next time.